Hey guys, so I am back, and this week we will be talking about lesson 3.4, also known as a lesson on coordinates. Okay, so when I say coordinates, what I mean by that? Well, we're going to get to it. That's not right. Okay, we're going to pretend that didn't happen. Okay. So coordinates. We're going to start out with an example. Not that color, or not that size. Okay. So we start out with the idea of vectors, v1, which is equivalent to 1, 1, 1. And then the vector v2, which is equivalent to 1, 2, 3, right? These are vectors in R3. And they define a plane V, which is the span of V1, comma V2. What the book wants to know is this vector X equaling 5, 7, 9? Is that in V? Is that in V? Well, the way that we would solve this is pretty easy, because what it's really asking is, do there exist scalars such that X equals C1 of V1 plus C2 of V2? In other words, is X a linear combination of the vectors? It's pretty easy to figure that out, right? Because you would just do a matrix, right? You'd set M, we're going to call it matrix M, equal to 1, 1, 1, 1, 2, 3, 5, 7, 9. And of course, we find the reduced row echelon form of this. 1, 0, 0, 0, 1, 0, and 3, 2, 0. So you might be asking, well, what does this matrix mean? Well, that means that X is on the plane for these scalars. C1 equals 3, and C2 equals 2. Right? So that X equals C1 V1 plus C2 V2 equals 3V1 plus 2V2. So then the book illustrates this geometrically. So it draws out a plane. This is a plane V. Okay, and we've got, no, that's not straight. Okay. So first we have our V2 and our V1. And all the way out here. So we've got 3V1, 2V2, and then of course, those dot out to here, 2X. Okay. So if we want to visualize the coefficients 3 and 2 in this linear combination, one thing that's really good to do is to introduce a coordinate grid with the axes pointing in the directions of the vectors v1 and v2. So in the grid, our vector would have the coordinate C1 equals 3 and C2 equals 2. So I can draw a grid if that's helpful. So we'll have 1, let's see, 2, 3, 4, so on and so forth. And this is a very badly drawn grid, but the purpose is that you can see, right? It's a color again. You can see that we're up 2, right? And we're over 3, which leads to here, which should technically be here. But that's besides the point. So what's the point of introducing this coordinate system? Well, that's because we can now define something called the coordinate vector. Coordinate vector of V1 of V equals 3V1 plus 2V2 is three, 2. In other words, it's defined by our C's. We can think of 3, 2 as the book describes it as the address of X in the C1, C2 coordinate system. Now, the way that we would notate this is when we've got the coordinate vector, we would call it this with a fancy little b. That should be a b. There we go. That is the way that we define the coordinate. So this, of course, leads us to a definition. So for any basis, V equals V1, and that's supposed to be the fancy V, V2 through Vm of a subspace V of Rn, it can be written uniquely as X equals C1 V1 plus C2 V2 all the way out to Cm Vm, right? So that means that the B coordinate is denoted by, I'm just going to say C notation. Continue this over here, C notation, where the coordinate vector is made up of all of the C's. Finally, we can say that X is equal to S times the coordinate vector, where S equals a matrix with column vectors that are our basis. In other words, S would look a little something like V1, V2, so on and so forth. Right? Let me clear this. Okay. So now that we know that, let's think about these coordinates, and we're going to think about their linearity, right? Because we always have to prove things linear or not linear, right? The next thing that we can say is that if we've got, I'll use my drawing here, vector X plus vector Y with that fancy little b equals coordinate vector X plus coordinate vector Y. Right? That's what we have to prove when we prove things linear. So that's the case. The second thing that we have to also prove is that if you've got the coordinate vector of kx, where k is a constant, that is equal to k times the coordinate vector of x. Now, the book only proves the second part because it's fairly straightforward. Sorry. got like a little tickle in my throat. Okay. Because it's fairly straightforward to prove the first part from there. So I'll show you. But basically, we've got K, it's vector X. That is our coordinate vector. And we can break it down, pick a different color again, into K, C1, all the way through K, C, M. But of course, from there, we can pull out the K, right? We know that with a vector, if we've got, a constant applying to every part of it, we can pull out that constant all the way to Cm. And if we were to condense that back down into the notation, it would become K times the vector coordinate. Okay. And like I said, you could prove for part A as well. It wouldn't be too bad. So now we have kind of a pretty simple example. It wants us to consider bases of R2 consisting of vectors C1 equals 3, 1. Obviously, you know this is not correct notation at all. And vector B2 consisting of -1, 3. Okay, so if we're told that x equals 10, 10, nope, that should be an equal size. Nope, 10, 10. They want us to find vector coordinate. And then they want us to go the other way. If the vector coordinate is 2, -1, find x. I don't really think that I have to go through all of the math here. I think I can just tell you how to set both of these up, right? So for part A, of course, for both of these, we're going off with this very simple equation. Right. So for the first one, we would set it up so we've got 10, 10 equaling C1 of 3, 1 plus C2 of -1, 3. And of course, for the next one, it would be really simple, right? We would have, let's see. What am I doing here? Okay, so we'd have x is 2 b1 plus -1 v2, and then we plug in what we know v1 and v2 are, and that's how we would find x. So that's really simple. The book just kind of wanted to go over the basics, right? Let's see. What is the next thing that we're doing here? Okay, this example confused me a little bit, so bear with me. We're going to do the best that we can, but forgive me if I get a little confused along the way. But we're going to say that L, right? It's a line in R2. And it's spanned by the vector 3, 1. T is the linear transformation involved here from R2 to R2 that projects any vector X orthogonally onto line L. Okay. They say that we can facilitate a study, let's see, of T by introducing a coordinate system. And they mean a coordinate system where L is one of the axes, right? We've got L equaling the C1 axis with a C2 axis perpendicular to L. We can use this coordinate system, right, to say, if this is true, then T changes C1, C2 into C1, 0, right? Because of course, if it orthogonally projects, then there isn't going to be any C2 involved, right? It'll be on the line, right? And of course, that means that our matrix B is going to be 1, 0, 0, 0 is our transformation matrix. We'll say it equals T, right? And you can check that if you want, but if you do 1, 0, 0, 0 times C1, C2, that just gives you C1, 0. All right. So for here, sorry guys, I'm yawning a lot. I really apologize for that. Yeah, okay. Okay, so the book then goes on to make these ideas more precise. If you're getting a little lost right now, just keep in mind this is all leading up to a theorem. So yeah, we figured out this matrix T, and they want to make these ideas more precise. So we've got a basis of V1, comma V2, right? V1, comma V2. And if we want to follow the rules of what we've been saying, we got to make one of them on the line L and one of them perpendicular, right? So we've got V1 is 3, 1, and V2 is -1, 3. Right? So then if X is going to equal C1, V1 plus C2, V2, I'll highlight here. So this is on L, and this is perpendicular to L, right? So if we know that our transformation, right, is the projection onto L of X, because that's the definition of an orthogonal projection, that means that T of X equals C1, V1. Okay. So that means that if we're thinking about our C coordinates are going to be 1, 0, right? Which means that we can define another sort of vector coordinate, which is the coordinate of T of, so that means that we can define a new type of vector coordinate, which is the vector coordinate of T of X equaling C1, V1. Okay. So that means that the matrix B, or T, equaling 1, 0, 0, 0, transforms the vector coordinate of B, which is C1, C2, into the vector coordinate of T of X, which is C1, 0. So I'm going to clear these drawings and explain a little diagram that can be really, really helpful. So we can set X equal to what should be familiar now, C1, V1, plus C2 V2. And this will be a example specific diagram, but it can be extended. It can be extrapolated out to a lot of different examples. So that leads to T of X equaling C1 V1. And we can extend that to coordinates, right? So we have got the vector coordinate X which equals C1, C2. And then we've got B, which equals 1, 0, 0, 0. Same thing as T, right? These are equivalent. And that leads us to our other vector coordinate, T of X, which equals C1, 0, right? And so you can see the connection between these two things, right? So these vector coordinates are based off of sort of like the pre-transformation and the post-transformation, or I guess you could call it the input and the output kind of generally. So that leads us to another theorem, which is titled the matrix of a linear transformation. Okay. So if we have a linear transformation T from Rn to Rn and a basis B equaling V1 all the way to Vn Rn, that means that there exists a unique n times n matrix transforms the vector coordinate of x into the vector coordinate of T of x, or notated T of x vector coordinate can also be written as B times x, the vector coordinate x, which makes me realize that I misspoke earlier. So let me make a big point of clarifying. When I refer to this, right, I refer to it as the T matrix. That is incorrect. This is a matrix that is transforming strictly from here to here. It's transforming from vector coordinate to vector coordinate. So that is not the same thing as your standard, what we'll call later the A matrix, that transforms from just does your regular linear transformation, right? Basically, you've got three different types of matrices. There's A, S, and B, right? And A is like your very standard matrix that, transforms from input to output. It does the linear transformation. We've been working with that a lot. S, like we said before, is the one made up of the bases as the columns. And then B, of course, is the one that transforms from coordinate vectors. So just definitely don't let me confuse you on that front, because that's definitely very important. So anyway, back to what we were doing. Based on this, the book further clarifies that we can write this B matrix as a situation where each of the coordinates is the vector coordinate of T of V1, the vector coordinate of T of V2, and so on and so forth for all of the columns. And that is how we can define this B vector. And of course, I will show you how to compute this in a minute. All right. So we can prove this now, of course. Because if we know, based on, the proof that we already had, if we start out with this vector coordinate of the transformation, we can, of course, split that apart, right? And define it as T of C1 V1 plus C2 V2 all the way up to Cn Vn. That's because, of course, we know that's how X is defined, right? Then from there, we can pull some stuff out, right? We can pull out these C's. So we can do, because they're constants, right? We can always move constants around. So C of T of V1 plus all the way down the line to Cn of, or Cnt of Vn. That vector coordinate. Then we can do some more moving. We can pull C out even further and do C1 of T V1 vector. And then plus all the way down the line to Cn of T of Vn, that vector. All right. And from there, we can write this in a different form, which is one where we've got these matrices made up of the vector coordinate vectors of T of V. Going all the way to Vn. And we've got, of course, this matrix, and then we multiply it times C1 through Cn. Well, that C1 through Cn should look familiar, because we can define both of these things in much simpler ways, right? So we can define this as B and define this as the vector coordinate, or the address of X. So, in other words, T of X, the vector coordinate of T of X is equal to B times the vector coordinate of X, right? I'll highlight, because in case you forgot where we were trying to go with this, we were trying to prove that that is equal to this, right? Which we did successfully. So yay for us. Okay. So now that we've done that, we're going to look at an example of how we would actually go about implementing all of these things within a problem. Oh, I think I've hit that point of the night where I'm not tired anymore. So that's good, which means you might have to hear me yawn less. So that's always good. So we want to find the basis B equals V1, V2, V3 in R3, where V3 is equal to V1 times V2. And the reason this is the book pointed out to take a look at theorem A10 in the appendix to review the basic properties of the cross product. So basically what that means is that V3 is perpendicular to V1 and V2, right? That should be pretty straightforward. That also means that you can say that V3 is a unit vector because of just like facts about the cross product. But that's not incredibly important. So What is important is drawing an image here. So what they want us to do is find the V matrix of the linear transformation of x equals v1 times x. Okay, so we're going to start out with a little chart. So first, let's think about what we know geometrically. So we've got a v1, right? We've got a v2, right? And they're perpendicular to each other, and v3 is perpendicular to both of them. And then we can extrapolate that out even further to explain that we can say that if you've got v1 times v3, right, that equals negative v2, right? And that just makes sense. Here, I'll highlight this to show it, but if we think about it in the sense that you take these two, right, and you get this, right? So if you take these two, if you kind of flip your orientation around, in fact, you can even imagine sort of flipping this upright in a sense. And so, of course, this will be the vector that's perpendicular to both of these. So, armed with this information, we want to figure out the B matrix, right? So how are we going to go about doing this? Well, we're kind of going to make that chart, that chart that I showed you earlier that was kind of handy dandy for looking at all of this stuff. So we're going to have X being equal to C1 V1 plus C2 V2 plus C3 V3. And you perform some transformation T, right? And we know that T of X1 equals V1 times X. Well, we can write X out like we just did as C1 V1 plus C2 V2 plus C3 V3, which we can then further split into C1 times V1 plus C2 V1 times V2, and finally C3 of V1 times V3. So we've done that, right? Well, that means that we can do the second part of the chart now. We start out with this, right? Our coordinate vector X, which of course equals our C1, C2, C3. And then we can also say that T of X1, or T of X, sorry, that vector coordinate is, think about this, what are our C's going to be? Well, if we think about how can we simplify, just chose the same color. How can we simplify this? We just went through all that trouble of drawing this graph right here, right? So C of V1 times V1, well, that's going to be 0, right? Because V1 times V1, if they're perpendicular, then it's going to cancel out. This one, right, is going to be C2 of V3. And this last one is going to be minus C3 of V2, right? Well, what's nice is that this right here tells us where to put these C's. What I mean by that is you've got 0, right? But instead of just putting the next one in order, instead of putting C2, you're going to put negative C3, right? Because it's in the spot of V2. That might be slightly confusing, but if you look at this, it should not be. And then the last one is C2. And that is your T of X vector coordinate. So of course, our B, our final B, is just going to be moving from this to here, right? So we can write that as B equals 0, 0, 0, 0, 0, 1, 0, negative 1, 0, right? But there is one other way that we can get this, which is to construct B column by column. So what do I mean by that? We've already got this fact, right? We've got that B equals a matrix where the columns are the vector coordinate of T of V1, the vector coordinate of T of V2, and the vector coordinate of T of V3, right? And these acting as our columns. So we have to figure out is these three things, right? We have to figure out what T of V1 is, T of V2 vector coordinate, and T of V3 vector coordinate. So we already know that T of V1 equals 0. T of V2, I'm just shortening, T of V2 equaling V3, and T of V3 equaling negative V2, right? Which means that we can figure out these columns. This column is going to be 0, 0, 0. This column, 0, 0, 1. This column, 0, negative 1, 0. And that way you can get the exact same vector, right? Which is really quite simple. And one final thing that can be helpful if all of this is still not intuitive to you is you can think about it right like this. Let's write out our B matrix again. 0, 0, 0, 0, 0, 1, 0, negative 1, 0. Along the top, you can write T of V1, T of V2, T of V3. And along here, you can write V1, V2, V3. And you can verify this if you want, but it's true. If you look at it from this angle, this is V1, this is V2, and this is V3. And if you look at it from this angle, T of V1, T of V2, T of V3. I'm not going to go through the whole process of just like checking, but yeah, that's a helpful way to look at it, I think. So let's see, what is our next example? And do we really need to do it? I feel like a lot of the examples in this chapter are a little bit redundant. Let's see, this one is, we've got the linear transformation from R2. Yes, this one is actually important. So we will do this one. Sorry, that's not sounded snarky. I was like, this one is actually important, but they're all important. And I actually do find the majority of the examples in the text to be very informative. So we have T equals the linear transformation from R2 to R2 that projects any vector orthogonally the line outspanned by the vectors 3, 1. Right? And before, back in example 3, we found that the matrix of B of t, if you have a basis of 3, 1, negative 1, 3, is 1, 0, 0, 0. So in this case, we want to know the relationship between B and the standard matrix A of t, right? And I already told you, we thought about those 3 matrices. We've got A, B, and S, right? And A being just like that average matrix that turns, that does the transformation, the one we've been working with, throughout this whole course. So the way we can think about this is we have to recall a couple of things. The first one, we have to recall that X is equal to S of the vector coordinate B or X, where S in this case, right? What would S equal? Well, since it's V1, V2, it would be 3, 1, negative 1, 3. So we can think of this following diagram. Diagrams are really helpful in this chapter. I actually think they're really helpful in general. The book will include them sometimes, and they can be really good about visualizing because, if you really think about it, linear algebra is just transformations. It's mapping from some dimensions to other dimensions. It's just transformations, right? So it's really helpful to have, I think, diagrams that show that, and they can do that really effectively. So let's see. In this diagram, we start out with X, and we apply A, and that's how we get to T of X. Down here, we've got the vector B, or the coordinate vector X. If we apply S, we get X, right? Here we've got B that takes us to the coordinate vector of T of X. And again, if we apply S to this thing, we get back to the T of X, right? So we can look at this and point out and notice the T of X, is equal to A times this, right? Because this does equal X, right? And X, A times X is T of X, which is the same thing as S times B times this. Right? So that's how we get these very important relations. AS equals SB. B equals inverse of S times AS. And A equals SB inverse S. So if we move back to the example we had at hand, and we don't really have to do all the math and everything, but just understanding the basics, we would have A equals S, the S inverse, which would equal 3, negative 1, 1, 3 times 1, 0, 0, 0. And of course, the determinant, which would be 1 over 10 times D B negative B A, no, DB negative CA, right? And we would eventually get to the matrix 0.9, 0.3, 0.3, 0.1. All right. Okay. So that leads us into an idea of similar matrices, and this is the last thing that I'm going to do tonight. And the only thing that we'll have left for tomorrow that I'll kind of add is some stuff on diagonals, right? And of course, also problem sets. I have not done problem sets in a while. They've kind of taken a backseat to me just getting through I've done problem sets on my own. I'm sorry, I haven't posted about problem sets in a while. So I have some good questions kind of picked and chosen from all over the last couple of units, but I actually think that can be kind of good because it keeps us on our toes and it reminds us of things that we learned before. And, you know, all of these things are used together. They're not used in isolation. So just like going problem set by problem set, you kind of lose, I think, seeing all the connections. So hopefully that will help with that a little bit actually. But we'll end with the idea of similar matrices. If you consider two matrices, A and B, say that A is similar to B if there exists an invertible matrix S such that AS equals SB or B equals S inverse times AS, right? So I'll just kind of show how you solve these, which is quite simple. So you have, let's imagine that we've got a matrix A, which equals 1, 2, 4, 3, similar to B equals 5, 0, 0, -1. Like we want to find out if these two are similar. How do we do that? So we're looking for a matrix S, right? And we're just going to assign random variables here, S, where we've got X, Y, Z, T, such that this relationship is true, right? So what they describe it as a brute force method because it's, you know, it's not a particularly beautiful sum notation or, you know, just very abstract method. But a way that we can do this is we set S times A equal to S times B, which would be X plus 2Z, Y plus 2T, 4x plus 3z, 4y plus 3t. And we set that equal to 5x, negative y, 5z, negative t. And then from there we solve. And eventually we get that z equals 2x and t equals negative y. In other words, these two matrices are similar as long as we've got the matrix S that equals x, y, 2x, negative y. So that's kind of your basic method for figuring out if the matrices are similar. So I'm going to come back tomorrow, obviously. I'm going to add more to this. I'm going to add problem sets. I'm going to do more. But this is just kind of a little update on 4.1, around 3.4. Currently, I am on 6.1, which seems like a huge leap, but that's just because we did not do 4 or 5. The way the book is set up, for full transparency, is just that you can sort of jump around a little bit. You have to do 1, 2, and 3 to get the basics, right? But then from there, you can go into sort of more specific topics. And we chose to jump into 6, which is all about determinants, just a whole chapter on determinants. And then we'll be doing something called eigenvalues and eigenvectors, which is 7. I don't really expect to get through every single chapter in 7 because there are 6 like individual chapters within the larger chapter of 7. But yes, that's where we're headed. and then we'll be done. That'll be the end. But yeah, that's kind of what's going on and where we've been and where we're going. So I hope this has been informative. Thank you so much and have a lovely week.